Welcome to Sleepy Stories, where the mind can wander through knowledge as the body settles into rest. This is a place to learn gently, to drift between understanding and calm. You do not need to stay awake to follow every detail. The story will continue even if your thoughts begin to blur. If sleep does not come immediately, there is no need to chase it. Let the rhythm of ideas and the quiet pace of explanation carry you. And if these nights of curiosity and calm help you, we invite you to like and subscribe so that more evenings can end with light, learning, and peace. Tonight, we begin beneath the calm sky of the far north, where curtains of color sometimes appear without warning. They rise and move as if the air itself had learned to glow, green veils that ripple, red edges that fade into violet arcs. This is the Aurora Borealis, the northern light, a meeting point between earth and sun. What seems delicate and silent is in fact the visible trace of immense forces stretching across space. Each line of color begins 93 million miles away, in the heart of our star. At the center of the sun, hydrogen atoms are pressed together by gravity until they merge, forming helium and releasing energy. Most of that energy travels outward as light and heat, but some escapes as charged particles, electrons and protons streaming constantly into space. This flow is the solar wind, a faint but steady current that fills the solar system. It moves faster than any sound could travel through air, yet it carries no noise, only magnetic structure and momentum. Space, though we often call it empty, is filled with this invisible breath. Every second, the sun sends billions of tons of plasma into the dark. The planets drift within that outflow, and Earth, small and magnetic, resists it with its own field. Deep beneath the surface, molten iron turns slowly inside the planet's core, creating a magnetic field that extends far beyond the atmosphere. It forms a shield, the magnetosphere, which protects life from most of the solar wind's charged particles. Yet the protection is not absolute. Where the magnetic field lines curve down toward the poles, they act as open doors. Some of the solar wind follows these invisible paths, spiraling inward until it meets the thin air of the upper atmosphere. There, at heights between 100 and 300 kilometers, collisions occur. Fast electrons strike oxygen and nitrogen atoms, transferring energy and leaving them momentarily excited. When those atoms relax back to their normal state, they release photons, tiny flashes of light that, together, form the aurora's glow. Each color corresponds to a specific reaction. Oxygen, high in the atmosphere, emits deep red light, while lower oxygen produces the bright green most people recognize. Nitrogen adds violet and blue at the edges. Seen from space, these emissions form broad rings around both poles, constantly shifting in brightness and size as Earth's magnetic field interacts with the sun's variable output. From the ground, the effect is graceful and unpredictable. Pillars of light that twist like slow rivers, arcs that ripple and dissolve, faint flickers that appear and fade within seconds. Long before science explained these lights, humans watched them with wonder and sometimes fear. Arctic travelers wrote of spirits dancing across the sky, of silent fires, of messages from the dead. In every age, people looked upward to interpret meaning in color and motion. Now we know that the aurora is neither omen nor miracle, but the natural signature of electromagnetism at work, a reminder that our atmosphere is not separate from space, but part of a larger, connected system. Still, knowledge does not erase beauty. Understanding the mechanism only deepens the sense of calm that such precision exists at all. The same equations that describe electron motion also describe radio waves and the glow of nebulae light years away. Physics links the smallest particle to the widest horizon, and the aurora is where those scales touch, cosmic energy expressed as quiet motion above our heads. As you listen, imagine that distant energy arriving gently through the dark, bending along invisible lines until it meets the sky above the poles. It moves without sound, transforms without haste, and leaves only light in its wake. In the vastness between sun and earth, this simple exchange continues endlessly. You may let that rhythm settle into your breathing, steady, unhurried, balanced, and so, as the first faint shimmer rises across the horizon of thought and air, the story begins. From the glowing surface of the sun, a constant stream of charged particles flows outward into space. This stream is called the solar wind, and it is one of the most continuous movements in the solar system. The particles are mainly electrons and protons, the building blocks of plasma, which is matter so hot that atoms cannot hold on to their electrons. Every second, millions of tons of this plasma escape from the sun's outer atmosphere, the corona. Despite such numbers, the solar wind is exceedingly thin, less than a whisper compared with any air on Earth. A spacecraft flying through it would find only a few particles in every cubic centimeter. Yet because each one moves at hundreds of kilometers per second, together they form a powerful flow of energy and magnetic influence. The journey begins in a region of extreme heat, where temperatures exceed 1 million degrees Celsius. The gas there is fully ionized, meaning electrons move freely among nuclei. Pressure and magnetic forces propel the plasma outward. As it moves away from the sun, it expands and cools, but never stops. It carries embedded magnetic fields, twisted and shaped by the sun's rotation. These fields spiral through space in great arcs, creating what scientists call the Parker spiral, a vast magnetic pattern that fills the solar system like an invisible web. Through this structure, the solar wind travels endlessly, forming the heliosphere, a bubble that reaches far beyond Pluto. Within this bubble, every planet lives inside the sun's extended atmosphere. The solar wind defines the boundary between our star's influence and interstellar space, a frontier called the heliopause. Cosmic rays from other stars strike this boundary and are deflected or slowed. In that way, the sun shelters its planets, not just with light, but with an unseen magnetic cocoon. Closer to Earth, the solar wind's behavior becomes more complex. When its magnetic field points opposite to Earth's own, the two fields can connect in a process known as magnetic reconnection. This allows energy and particles to enter the magnetosphere, sometimes triggering bright auroras or strong geomagnetic storms. Scientists monitor this interaction with satellites, such as the Solar and Heliospheric Observatory and the Parker Solar Probe. These instruments measure the speed, density, and direction of the wind, turning space weather into a measurable science rather than a mystery. The motion of the solar wind is not constant. It varies with the sun's activity cycle. During solar maximum, sunspots multiply and flares erupt, throwing bursts of plasma called coronal mass ejections into space. These immense clouds travel outward and can reach Earth in 1 to 3 days. When they arrive, they compress the magnetosphere and inject new energy into it, intensifying auroras. Even when the sun appears quiet, smaller streams emerge from holes in the corona, producing fast and slow solar wind regions that interact and create waves and shocks in space. Although the solar wind is invisible, its presence can be felt through its effects. It shapes the tails of comets, sweeping dust and gas into long luminous streams that always point away from the sun. It sculpts planetary magnetospheres into teardrop shapes, compressed on the day side and stretched behind. It even influences the movements of interplanetary dust, slowly pushing particles toward or away from the sun over thousands of years. Through such constant pressure, the solar wind becomes a quiet architect of planetary space. In scientific laboratories on Earth, researchers recreate miniature versions of this plasma to study its properties. By understanding how charged particles move through magnetic fields, they improve models of auroral formation and protect satellites from radiation damage. What happens between the Sun and Earth is not chaos. It follows equations describing magnetohydrodynamics, the physics of fluids that conduct electricity. Within those equations lies a kind of serenity, forces balanced, motion continuous, every line of magnetic field following its natural curve. If one could watch the solar wind without instruments, the sight would still appear calm. There are no flashes, no sound, only a steady expansion of energy into silence. In that calm, the seeds of the aurora are carried across millions of kilometers. Each particle leaves the sun's surface with enough speed to reach Earth in a few days, yet the journey is unhurried by any measure of cosmic time. Light itself takes only 8 minutes to arrive, but these travelers of plasma take their time, drifting in the magnetic current that connects star and planet. You may imagine them now, billions of tiny points of matter moving through the blackness, drawn along unseen spirals of force. They will soon meet Earth's magnetic shield and paint the sky with light, but for this moment they are still in flight, suspended in quiet motion. Their journey is continuous, their destination inevitable, and their rhythm steady enough to ease a restless mind. The universe moves, but it never hurries. The science is exact, the light is real, and the calm that follows is yours to keep. Around our planet extends a vast, invisible structure, a magnetic shield that guards every living thing from the solar wind's charged storm. It is called the magnetosphere, and it begins deep within the planet itself. Far below the crust, molten iron and nickel churn in the outer core. These metallic currents create electric currents, and electric currents generate magnetic fields. Together they form a self-sustaining dynamo, turning the entire Earth into a giant magnet with a north and south pole. From those poles, magnetic field lines rise through the crust, stretch far into space, and loop back again, creating a protective cocoon that moves with the planet as it orbits the sun. If one could see the magnetosphere, it would appear like a teardrop. On the side facing the sun, the solar wind presses hard, compressing the field to a distance of only about 10 Earth radii. Behind the planet, the field stretches outward for hundreds of radii, forming a long magnetic tail called the magnetotail. This shape constantly changes as solar wind pressure rises and falls. The magnetosphere is not rigid but flexible, an elastic shield that bends, reconnects, and reforms in response to external forces. The boundary where the solar wind first meets Earth's field is known as the bow shock. Here, supersonic plasma slows abruptly, converting kinetic energy into heat and magnetic disturbance. Beyond it lies the magnetopause, the outer surface of the magnetosphere, where solar and terrestrial magnetic fields balance each other. This region is crucial. Most charged particles are deflected here, streaming harmlessly around the planet. Only a fraction find paths inward through polar regions, guided by lines of force that converge near the magnetic poles. Inside this protective space lie the Van Allen radiation belts, two donut-shaped zones filled with high-energy electrons and protons trapped by magnetic fields. They oscillate between north and south, bouncing along field lines while spiraling around them. Though invisible, these belts are carefully monitored because their radiation can damage satellites and endanger astronauts. Their existence demonstrates that Earth's field not only shields life but also stores and channels energy, like a vast natural capacitor. Magnetometers on the ground continuously record subtle variations in the field's strength and direction. When solar activity intensifies, these instruments detect sudden disturbances known as geomagnetic storms. Auroras bright enough to be seen at mid-latitudes are one sign of such events. For scientists, each fluctuation is a clue to the dynamic relationship between solar wind and planetary magnetism, a conversation written in lines of force instead of words. The mechanism behind this protection is elegantly simple. Moving charges experience a magnetic force perpendicular to both their motion and the field itself. This deflection bends their paths, preventing most from penetrating the atmosphere. Mathematically, it is described by the Lorentz force, an equation as graceful as it is universal. The same principle guides electrons through a laboratory magnet and steers cosmic rays away from living cells. Nature's consistency offers quiet reassurance. Everywhere, the same rules apply. From orbit, satellites equipped with magnetometers map this invisible geometry. Their data reveals structures within the magnetosphere, the plasma sheet, the cusp regions, and the ring current that ebb and flow with solar conditions. When magnetic reconnection occurs, energy stored in twisted field lines is suddenly released, accelerating particles toward the poles. These bursts eventually light the sky, yet the foundation remains this steady magnetic order. For the people who study it, the magnetosphere is both shield and teacher. It shows that strength does not mean immobility. True stability lies in the ability to yield and recover. The field bends under solar pressure, then springs back, preserving equilibrium. In that balance is a lesson about resilience, force met not with resistance alone, but with flexible harmony. As night settles across polar regions, this invisible architecture quietly stands guard. Billions of particles from the sun are deflected each second, their paths curved outward like rain sliding off a dome. Only a few find the narrow corridors that lead toward the poles, where air and energy will soon meet to create light. The rest drift away into space, their motion absorbed by the calm persistence of a planet's magnetic breath. If you imagine Earth from space, wrapped in its faint blue halo, picture also this unseen structure embracing it. No sound marks its presence, no color betrays its shape. Yet it works constantly, day and night, ensuring that life can thrive beneath the sky. Every compass needle, every migrating bird, every aurora owes its existence to the same steady engine deep within the earth. And as that core continues to turn, the shield endures, an unbroken conversation between fire and silence, motion and calm. Where Earth's magnetic field narrows toward the poles, invisible corridors open into space. These are the regions where charged particles from the solar wind can enter the atmosphere. Instead of striking directly, they follow curved magnetic field lines, spiraling inward like travelers on a winding road. The reason for this behavior lies in the nature of charged motion. When an electron or proton encounters a magnetic field, it is deflected at a right angle to its direction of travel. The result is a helical path, a spiral that circles around the line of force while moving along it. This geometry turns the field lines into invisible highways connecting space to sky. As the solar wind presses against Earth's magnetosphere, it injects streams of particles into the magnetotail on the night side of the planet. There, energy accumulates until magnetic reconnection releases it suddenly, flinging particles back toward Earth at immense speeds. These bursts are guided along field lines that intersect the atmosphere near the poles, forming the auroral ovals. Although the process sounds violent, its rhythm is precise and predictable, governed by electromagnetic equations that conserve both energy and symmetry. When these high-energy electrons descend, they encounter denser air. Collisions multiply rapidly, converting kinetic energy into light. But the first stages of their journey are silent. They move through near vacuum, their paths defined not by sight, but by mathematics, Lorentz forces, vector components, and field gradients. Scientists visualize these motions using supercomputer models that trace millions of trajectories simultaneously. The result is an ever-changing pattern of arcs and spirals, elegant in its order. What appears as chaos in the night sky is, in truth, the visible result of invisible precision. The poles act as mirrors of each other. When auroras occur in the northern hemisphere, corresponding events appear almost simultaneously in the south. This symmetry arises because Earth's magnetic field is global. It channels energy along both ends of the same lines. The northern lights and southern lights are two views of one connected system. Observatories in Norway and Antarctica often record matching pulsations, their data separated by half a planet but synchronized in rhythm. Scientists studying these interactions speak of field-aligned currents, electric flows that connect the magnetosphere and ionosphere. These currents, named after Christian Birkeland, complete the circuit between space and Earth. They carry energy that sustains the aurora and subtly affects radio propagation and satellite drag. Each pulse through this vast electrical system links solar wind pressure to terrestrial response, forming what researchers call geospace, the combined environment of planet and star. The beauty of this process lies in its constancy. While solar storms come and go, the pathways remain. The field lines are redrawn each moment by the balance of internal and external forces, yet their structure endures. It is a living geometry, a system always changing yet always itself. The poles are not points but gateways, through which energy from the sun is exchanged with Earth's atmosphere in a continuous dialogue of motion and light. In the stillness of polar night, instruments record these events without sound. Magnetometers detect minute fluctuations, radars trace ionized layers, and satellites watch the oval glow expand and contract. To the human eye, the aurora seems to wander, yet behind every wavering arc lies a precise map of field strength, plasma density, and magnetic tension. The dance of the lights is therefore not random movement but visualization, a portrait of the planet's magnetic soul responding to the sun's touch. The air at these latitudes is clear, cold, and dry. When auroras appear, they seem close enough to reach, though they hover hundreds of kilometers above. People often report a sense of scale collapsing, as if the heavens had descended. In a sense they have. Through the aurora, outer space becomes briefly visible from the ground. Each pulse of color is a signature of distant physics, the path of an electron, the orientation of a field line, the whisper of a solar current translated into light. The quiet order of this phenomenon invites reflection. Our world is not sealed off from the cosmos. It is part of it, the same field that guides a compass needle guides particles from the sun. The same forces that steer electrons through circuits shape the glow above the Arctic. When one understands this connection, even a storm of charged plasma becomes something tranquil. Nature, in its precision, replaces fear with calm recognition. As night stretches across the poles, these invisible roads remain open. Electrons continue their journey, unseen yet ceaseless. They spiral downward, collide, and vanish into light, their paths recorded in silence. From orbit, Earth glows faintly at both ends, the auroral ovals shining like rings of slow fire. It is a reminder that even within darkness, order persists, a geometry of protection and grace that never truly sleeps. High above the Earth, where air becomes thinner than any mountain peak could reach, the solar wind's travelers finally meet resistance. At altitudes between 100 and 300 kilometers, electrons descending along magnetic field lines collide with atoms of oxygen and nitrogen. Each collision transfers a pulse of energy, pushing those atoms into an excited state. They cannot remain so for long. Within fractions of a second, they release the extra energy as light. This process, excitation followed by emission, is what turns invisible particles into visible color. In this thin layer, night becomes luminous. Physically, the mechanism is simple, yet its scale is immense. Every aurora involves countless billions of atomic transitions per second. Each transition emits a photon, and each photon adds a thread to the sky's fabric. Together, these threads weave sheets, arcs, and coronas of light that may span thousands of kilometers. The human eye perceives only a fraction of the glow, but sensitive cameras reveal ultraviolet and infrared emissions beyond vision. What we see as beauty is in truth data, a spectrum that describes the composition and temperature of the upper atmosphere. The oxygen atom is the most prolific artist in this display. At about 100 kilometers altitude, it radiates green light at a wavelength of 557.7 nanometers, the hue most associated with the aurora. Higher still, near 200 kilometers, it releases deep crimson light at 630 nanometers. Molecular nitrogen contributes violet and blue edges, the result of electrons exciting the molecule's outer shells. Each color corresponds precisely to an energy difference between atomic states, and those differences act like fingerprints. Spectroscopy of auroral light allows scientists to measure altitude, density, and even wind speeds in the upper atmosphere without sending instruments into it. The thin air in which this glow occurs is called the thermosphere. Here, temperature is defined not by how warm it feels, but by the speed of individual particles. During strong auroras, those particles can move so fast that the temperature reaches several thousand degrees Celsius. Yet because the air is so rarefied, a human hand would feel nothing. Heat and cold lose meaning where matter is sparse. Motion exists without sensation. Above the thermosphere lies the exosphere, where particles escape into space, while below is the mesosphere, where meteors burn. The aurora occupies the boundary between Earth and the void, a luminous membrane separating air from vacuum. Instruments aboard satellites watch these interactions from above. They detect bursts of ultraviolet radiation, measure particle flux, and trace the geometry of magnetic field lines as they twist and reconnect. On the ground, arrays of all-sky cameras capture real-time images from multiple angles, allowing researchers to build three-dimensional models of auroral structures. In these models, light is not decoration but information. Each flicker corresponds to a change in current, a rearrangement of plasma, or a pulse of energy traveling through the magnetosphere. For scientists, the aurora is a natural laboratory. No man-made device can replicate such vast electric fields or such subtle variations in density. By observing these lights, researchers test theories of plasma physics and magnetohydrodynamics. They study how energy moves between charged particles and neutral atoms, how electric currents close through the ionosphere, and how these processes influence communication signals and satellite drag. Each observation refines our understanding of the space environment that envelopes the planet. To the eye, however, none of this complexity matters. The experience is immediate and silent. The lights appear to move, yet their motion is an illusion created by shifting patterns of excitation. What one sees as a flowing curtain is in fact a series of local emissions turning on and off faster than perception can separate. The result is fluid grace, nature's version of a slow heartbeat written in photons. In remote regions, where city lights never reach, the aurora can be bright enough to cast shadows on snow. Under that glow, time itself seems to pause. Every aspect of the aurora's appearance follows physical law, yet nothing about it feels mechanical. The balance between particle energy, magnetic guidance, and atmospheric composition produces an order that seems effortless. When one learns the equations that govern it, conservation of energy, electron excitation, cross-sections, magnetic mirroring, the mystery does not vanish, it simply changes form. Wonder becomes precision, and precision becomes another kind of wonder. If you picture the scene from above the Earth, the spectacle is even more complete. Two rings of light encircle the poles, faintly pulsing as solar energy flows through the magnetosphere. Between those rings, continents sleep beneath clouds, unaware that space is painting their horizons. The planet, shielded by its magnetic field, radiates softly into darkness, each photon a small act of equilibrium between the sun's power and Earth's calm resistance. The meeting of air and space is never violent. Energy arrives, is absorbed, and is released as light. Nothing is lost, everything transforms. In that transformation lies the quiet logic of the universe. Motion without sound, color without heat, change without destruction. What begins as fusion in a distant star ends as a flicker of green in our night sky. The chain of cause and effect is unbroken, and within it, the mind can find rest. In the deep Arctic night, the first signs of an aurora often begin as a faint glow, like a cloud that should not be there. It forms low on the horizon, green, grey, and still, then brightens until it becomes a ribbon that sways across the stars. To the eye it looks alive, yet it is nothing more than charged particles meeting air. Scientists call this quiet radiance the auroral arc, the simplest and most stable form of the northern lights. At about 100 kilometers above the ground, oxygen atoms emit the soft green light that defines most auroras. A few kilometers higher, thinner air allows red light to appear at the edges. What we see as motion is a chain reaction, millions of atoms excited and relaxed in rapid sequence as streams of electrons move along Earth's magnetic field lines. To cameras set on long exposure, these shifting bands trace the invisible geometry of magnetism itself. Measurements from ground stations show that the brightness of an aurora reflects the rate of energy transfer from the magnetosphere to the ionosphere. When solar wind pressure increases, the auroral oval expands, producing brighter and more dynamic patterns. During quiet conditions, it narrows into a calm ring that circles the poles. This predictable relationship allows scientists to estimate the strength of space weather from simple light measurements, turning beauty into data. Yet data do not capture the experience. Beneath the glow, the air feels colder, the world quieter. The ground reflects the color faintly, snow and ice taking on a green sheen. Sound seems to vanish, replaced by the slow rhythm of light brightening and fading. For those who stand in that stillness, the mind often mirrors the sky, thoughts slowing, attention widening, breathing easing into the same rhythm as the moving arc above. If sleep begins to draw near as you listen, let it come easily. The aurora will continue its silent work, whether your eyes remain open or closed. Each pulse of brightness is another exhalation of the planet's magnetic breath, steady and unhurried. The body understands this rhythm. It responds to repetition and calm patterns. Just as charged particles find their path along lines of force, rest follows the path of familiarity, guided by the same quiet consistency. When the aurora strengthens, the single arc splits into many. Curtains of light twist and fold, rising upward as if drawn by unseen strings. At times the entire sky seems to move, rippling in long waves that pass from horizon to horizon in seconds. High-speed cameras reveal that these movements correspond to fluctuations in electric currents flowing through the ionosphere. They are signatures of plasma waves, moving at thousands of kilometers per second yet appearing to drift slowly to the human eye. From space, the scene looks organized, almost mathematical. The polar regions glow in ovals that pulse in synchrony with bursts of solar energy. Satellites record these oscillations as variations in magnetic field intensity, each pulse part of an endless cycle. For the observer on the ground, that order becomes emotion, a feeling of connection to something vast and calm. Light flows where geometry allows it, and life, too, follows invisible structures of balance and return. As the night deepens, the green curtains fade and the stars reappear behind them. The process that created them does not stop, it merely becomes invisible again. Energy continues to travel, collisions still occur, but the threshold of visibility has passed. The sky seems to rest, and perhaps so can you. Every glow in the aurora begins with a collision. When fast-moving electrons from the solar wind enter the upper atmosphere, they encounter neutral atoms and molecules of oxygen and nitrogen. These impacts transfer energy, knocking electrons out of orbit and creating ions, atoms that carry a charge. This process, known as ionization, turns a region of cold, thin air into a plasma where charged and neutral particles mingle in constant exchange. In this plasma, light is the natural consequence of restoration. Each atom, once disturbed, seeks balance again. The simplest explanation lies in quantum physics. Electrons within atoms occupy defined energy levels. When an incoming electron excites an atom, one of its internal electrons jumps to a higher level. It cannot stay there. After a brief moment, it falls back, releasing a photon of specific color and energy. The hue of that photon tells the story of the transition: green for oxygen at 557 nanometers, red for oxygen at 630, purple or blue for nitrogen. The sky becomes a spectrum of subatomic decisions, each governed by immutable laws. In the laboratory, these same emissions appear when scientists run electrical discharges through gas. Neon lights, for instance, work on the same principle, though their confinement makes the light constant rather than fluid. The aurora is simply the open-air version, written across thousands of kilometers. The difference is scale. Instead of a glass tube, the magnetosphere itself defines the path. Instead of a power source, the sun provides voltage. Each second, roughly a trillion collisions occur within a bright aurora. Though violent on an atomic scale, they produce no sound, for the air is too thin to carry it. The entire event happens in silence. The calm one sees is real, even if the physics is energetic. It is a balance of opposites, motion creating stillness, disturbance yielding beauty. This paradox is one of the reasons auroras feel peaceful. Their violence cannot be felt, only seen. Instruments called spectrometers allow scientists to decode this light. By spreading it into wavelengths, they identify the gases involved and their altitude. The spectra also reveal how much energy electrons had when they entered the atmosphere. In this way, color becomes data again, a visible measure of invisible forces. Red light means high altitude and low energy. Green means denser air and stronger impact. The most intense storms mix these emissions into layers, making the sky appear textured and deep. Within these emissions lies the boundary between Earth and space. The ionosphere, a region of charged air between 80 and 500 kilometers high, reflects and absorbs radio waves. Its behavior changes constantly as auroral activity rises and falls. Communication signals may bend or fade, and satellite orbits can drift as atmospheric density fluctuates. What seems like art above us is, in fact, a global influence extending into every technology that depends on electromagnetic balance. There is order in this motion. Equations describe how electrons spiral along magnetic lines, how energy distributes itself, and how currents close through the ionosphere. None of these laws vary from night to night. The same patterns that governed the first aurora seen by ancient eyes govern every one today. In their predictability lies comfort, proof that even beauty has structure. When the aurora reaches its peak, the process of ionization becomes a kind of breath for the planet. Energy arrives, light expands, and then both fade as equilibrium returns. The upper atmosphere rests again, still charged, still alive, waiting for the next pulse from the sun. The cycle repeats endlessly, a slow dialogue between motion and calm that never truly stops. The aurora's color is not random decoration. It is the precise signature of altitude, chemistry, and energy. Each layer of the upper atmosphere glows in its own way, depending on what kind of gas lives there and how strongly it is struck by charged particles. Understanding this vertical structure turns beauty into measurement. It allows scientists to read the sky as if it were an illuminated graph. At the highest altitudes, around 200 to 300 kilometers, the air is so thin that collisions are rare. Here, oxygen atoms emit deep crimson light, the longest-lived of all auroral emissions. These photons are released slowly, over many seconds, because the transition that creates them is forbidden in ordinary laboratory conditions. On Earth's surface, where collisions happen constantly, this red glow would be quenched before it could form. Only in the stillness of the thermosphere can it shine. During powerful solar storms, these red auroras spread far beyond the poles, tinting entire northern skies like a faint dawn. Lower, near 100 kilometers, oxygen produces the bright green that defines most auroras. The air here is dense enough for collisions to be frequent, so energy transfers quickly, creating rapid variations in brightness. This layer is where the aurora moves and ripples, its features sculpted by turbulence and electric currents. Below this level, nitrogen molecules dominate, adding purple and blue edges to the curtains of light. Together, these emissions form a vertical stack of color, red at the top, green in the middle, violet near the bottom, a living cross-section of the atmosphere's composition. Scientists map these layers using spectrographs and triangulated cameras. By comparing the apparent height of different colors, they reconstruct three-dimensional profiles of the aurora. The results match predictions from atomic physics almost perfectly. Every hue corresponds to a known energy transition, every altitude to a defined atmospheric density. What looks spontaneous is in fact tightly ordered by the mathematics of collisions and decay times. The night sky becomes a vast, silent laboratory. The same principles help researchers study other worlds. On Mars, where the atmosphere is thin and mostly carbon dioxide, auroras appear in ultraviolet rather than visible light. On Jupiter, immense magnetic fields create bright ovals at far higher energies. By comparing these emissions, scientists learn not only about each planet's composition, but about the universality of physical law. Color becomes a common language across the solar system. The intensity of these hues also tells us about solar activity. During geomagnetic storms, when the magnetosphere is compressed and field lines reconnect, stronger particle streams penetrate deeper, making lower altitudes glow. Calm nights bring faint, high arcs of red. Disturbed nights produce fast-moving green and purple displays. Observatories track these variations to forecast space weather, helping protect satellites and power grids from electrical surges. The same lights that delight travelers therefore serve as signals for engineers and pilots, a natural alert system written in the atmosphere. Beyond their scientific precision, auroral colors have a quiet psychological effect. The greens calm the eyes, the reds seem to slow time, and the purples fade so gently they appear almost imagined. The human brain interprets these tones as safety rather than alarm, perhaps because they move slowly and lack sharp contrast. In a world of noise and motion, the aurora speaks through patience. It glows, fades, and returns, like a pulse too large to measure. When the display subsides, the memory of color lingers. The red afterimage in the eye fades last, echoing the long-lived transitions of the atoms themselves. Above, the oxygen and nitrogen settle back to equilibrium, and the upper air grows dark again. What remains is a kind of balance, a reminder that color itself is evidence of order, and order, when seen clearly, brings calm. The aurora does not simply appear. It moves, folds, and reshapes itself in patterns that obey the hidden structure of magnetic fields. Scientists classify these variations into arcs, bands, rays, and coronas, each form revealing the flow of energy through the upper atmosphere. To the observer, these shapes drift silently across the sky. To researchers, they are the visual language of plasma dynamics. The most common pattern is the auroral arc, a narrow ribbon of light that stretches from east to west. These arcs often mark the boundary between regions of opposite electric potential in the ionosphere. When that boundary shifts, the arc bends or splits, tracing the motion of charged currents far above. Sometimes these arcs fragment into parallel streaks known as rays. Each ray corresponds to a narrow column of electrons streaming downward along a field line, its brightness a measure of particle density. Together, they form curtains that shimmer like vertical threads in a moving loom. During strong geomagnetic activity, these patterns evolve rapidly. Waves of energy called Alphen waves travel along magnetic lines, shaking the plasma and causing the aurora to pulse. What the eye perceives as movement is often a chain of brightening and dimming regions that travel faster than sound but slower than light. Cameras that record the sky at high speed show complex oscillations, ripples running across sheets of green and violet as magnetic fields flex and release tension. These waves are the aurora's heartbeat, their rhythm controlled by the constant dialogue between solar wind and Earth's magnetic field. On rare nights, when conditions are perfect, the entire display converges into a single point overhead. This is the auroral corona. Lines of light radiate outward like spokes of a wheel, each marking a magnetic field line directed toward the observer's eye. The effect is mesmerizing and geometrically precise. The corona demonstrates the three-dimensional nature of the aurora. What seems to spread horizontally across the sky is actually a vertical structure shaped by the curvature of the field. Standing beneath one is like standing inside a vast dome of motion, surrounded by ordered chaos. Scientists studying these forms rely on triangulated photography and radar echoes to determine height and orientation. By comparing two views from stations hundreds of kilometers apart, they can reconstruct the aurora's shape in space. The resulting models reveal layered sheets tilted by electric currents and distorted by atmospheric winds. Each ripple in the light corresponds to a ripple in plasma density, proving that beauty and mathematics are inseparable in nature's design. Even the apparent stillness between movements tells a story. When the magnetosphere calms, auroras fade into diffuse glows that stretch evenly across the sky. These uniform emissions indicate steady precipitation of particles rather than sudden bursts. The transition from stormy arcs to quiet haze mirrors the balance within the magnetosphere itself, a system that, like a living organism, alternates between tension and release. Watching such changes invites reflection on scale. The patterns unfold over hundreds of kilometers, yet they obey equations defined at the level of atoms and electrons. Every twist of color is rooted in the smallest physical processes, yet visible across continents. This unity of size and law suggests something profound. Complexity does not break the rules, it displays them more clearly. As the aurora shifts and fades, the sky becomes a mirror for thought. Its shapes are fleeting, but their causes are enduring. The same motions will repeat tomorrow night and 1,000 nights after, written again in magnetic geometry. The lights remind us that nothing truly stands still, yet within motion there is constancy, a steady rhythm by which the universe keeps time in silence. At times, the sun sends more than its steady breath of particles. It releases sudden, massive bursts of plasma, known as coronal mass ejections. These eruptions travel outward through the solar system, carrying tangled magnetic fields that collide with Earth's own. When such an event reaches the planet, the magnetosphere compresses sharply on the day side and stretches deep into the night. The result is a geomagnetic storm, a temporary but powerful rearrangement of the planet's magnetic structure. The process begins when the magnetic field of the solar wind meets Earth's field at an opposing angle. Their lines of force reconnect, linking the two systems into one continuous circuit. Through these new connections, energy flows into the magnetotail, storing tension like a drawn bowstring. When the field lines in the tail snap and realign, the stored energy releases in a surge of charged particles. These particles race along the poles, striking the atmosphere and igniting the most vivid auroras seen from Earth. Scientists measure the intensity of such storms using indices like KP and DST, which track global magnetic disturbance. During strong events, compass readings can shift, satellites experience drag, and radio signals fade. Power grids may register currents induced by the changing magnetic field, occasionally leading to temporary blackouts at high latitudes. Despite their beauty, these storms are reminders that the aurora is not merely decoration, it is a byproduct of planetary-scale electricity. The magnitude of these disturbances can be immense. A single coronal mass ejection may contain billions of tons of plasma moving at over 1,000,000 kilometers per hour. Yet when its energy reaches Earth, the response unfolds slowly, like a tide. The auroral ovals expand toward the equator, sometimes visible in places where they are rarely seen: Scotland, Canada's southern provinces, even the northern United States. The sky becomes alive with arcs and rays, the colors deeper and faster than during calm nights. Instruments record spikes in energetic electron flux, while the quiet landscape below becomes illuminated by the faint glow of space weather. Despite their disruptive potential, geomagnetic storms are natural regulators in the Sun-Earth relationship. They release tension built up in the solar magnetic field and redistribute energy across the magnetosphere. In that sense, they are not anomalies, but expressions of balance. For scientists, these events offer opportunities to study plasma processes impossible to recreate on Earth. Every storm becomes a dataset: variations in current, particle velocity, and ionospheric heating, all teaching how energy travels through the cosmos. To the observer, though, none of this complexity is visible, only the light. Curtains of green sweep overhead, turning to crimson along the edges. The horizon flickers in pale violet. Some witnesses describe the sky as breathing, each expansion and contraction matching an unseen pulse of energy far above. This impression is accurate in spirit. The magnetosphere does breathe, its boundaries moving in and out with the rhythm of solar pressure. Within that breathing lies the same calm rhythm that guides sleep, a reminder that even vast systems find rest in cycles. When the storm subsides, Earth's field relaxes, returning to its usual shape. The lights fade to thin arcs, and instruments fall silent again. No permanent trace remains, only a record of numbers and the memory of light. The magnetosphere, like a living body, endures by yielding, absorbing stress, then letting go. What begins as turmoil becomes order, and in that transformation lies the quiet strength of our planet's magnetic heart. Long before instruments and satellites, people living under the northern skies learned to read the aurora as both mystery and sign. From the Arctic Circle to the northern coasts of Europe and Canada, ancient hunters, sailors, and storytellers watched the heavens ignite without knowing why. They gave the lights names drawn from their languages and fears: the fires that dance, the road of souls, the fox's breath. These early witnesses were the first to recognize the aurora as part of life's rhythm in the polar world. Archaeological evidence suggests that humans have observed auroras for tens of thousands of years. Cave markings and oral traditions across Scandinavia and Siberia describe the sky glowing with moving lights. In Inuit tales, spirits played ball with a walrus skull in the dark sky. In Norse legends, the lights were reflections of Valkyrie armor, guiding fallen warriors to Valhalla. Even in regions far south of the Arctic, written accounts appear when geomagnetic storms extended the auroral oval across continents. Chinese astronomers recorded red glows in their meticulous night logs more than 2 millennia ago, records that modern scientists can match to solar events reconstructed from ice core data. For centuries, the lights remained inexplicable. They were treated as weather, as celestial fire, or as a reflection of ocean ice. Not until the 17th century did systematic observation begin. European explorers in Lapland noted that the lights often formed east-west arcs, aligned with the compass needle. That simple observation, light moving with magnetism, marked the beginning of auroral science. Later, scientists like Anders Celsius and Olof Hiorter used early magnetometers to record how the compass fluctuated whenever the sky brightened. They discovered that the aurora was tied to the Earth's magnetic field, though the link to the sun was not yet known. The 18th and 19th centuries brought more precise measurement. During polar expeditions, observers began documenting color, shape, and duration. Their sketches, some delicate, some hurried by freezing hands, became valuable records for future researchers. In these drawings, modern physicists can still identify specific auroral forms, stable arcs, curtains, diffuse glows. These early notes became the foundation for today's classifications, showing how careful attention can turn wonder into knowledge without diminishing its beauty. Even as science advanced, the emotional response remained the same. Those who watched the aurora felt a mix of awe and smallness. The colors seemed alive, their movement purposeful yet unreachable. Explorers wrote of standing for hours despite the cold, unable to look away. Modern researchers often admit the same reaction. The data they collect are precise, but the sight itself still silences thought. There is something in the aurora that defies the noise of explanation, a reminder that understanding does not replace wonder, it refines it. Today, networks of cameras across the Arctic monitor the sky automatically, yet the human impulse to watch endures. People gather on frozen lakes, city edges, and dark hillsides, hoping to see even a faint green shimmer. The act of watching connects us backward in time to those first witnesses who saw the same light and felt the same stillness. The sky has changed little, even as our understanding has deepened. When one stands beneath an aurora now, surrounded by instruments and digital screens, it is possible to sense that continuity, a quiet thread linking the first story told around a fire to the latest satellite transmission. Light travels through space and time, carrying both physics and memory. Every new generation that looks up becomes part of the same unbroken observation, proving that curiosity itself is one of Earth's oldest traditions. Before science traced field lines and measured plasma, the aurora belonged to imagination. For early humans, the night sky was a living book, and light across its pages carried meaning. In the far north, where long winter darkness breeds silence and reflection, people sought explanation in what they could feel rather than prove. The northern lights became omens, warnings, or blessings, an ever-changing mirror for human thought. Among the Sami people of Scandinavia, the aurora was sacred. They believed that speaking loudly or whistling beneath it could summon danger, for the lights were spirits who listened. Inuit stories describe souls playing games across the sky, their laughter echoing in the shimmering arcs. In medieval Europe, crimson auroras were read as signs of war or divine anger, recorded in chronicles alongside eclipses and comets. Across Siberia, shamans viewed them as paths between worlds, bridges for communication with ancestors. Every culture saw motion in the heavens and shaped it into narrative, light transformed into language. Modern anthropologists recognize a deep pattern in these myths. Each one connects the aurora to emotion, fear, hope, awe, and reverence. The colors and motion invite interpretation because they behave like living things, appearing suddenly, dancing, vanishing. Even without understanding their cause, people sensed their order. Myths in that way were an early form of science, structured attempts to explain what was seen, guided by observation and imagination rather than mathematics. Today, satellites and equations have replaced spirits and omens, but the emotional reaction endures. Many visitors to the polar regions still describe the lights in spiritual terms. Standing beneath an aurora, they speak of quiet connection, of feeling the universe move without sound. Scientists, too, often fall silent when the sky flares green above their instruments. Knowledge does not remove wonder, it simply changes its shape. What was once mystery remains mystery still, just measured now in nanometers and electron volts instead of myths. If you find yourself listening to this while sleep begins to drift closer, there is no need to resist it. The same patterns that guided ancient stories can guide your thoughts into calm. Imagine the slow arcs of light above an endless horizon, brightening and fading in steady rhythm. Let your breath follow that rhythm. Inhale with the rising glow. Exhale as it softens. The world has always used the sky to remember how to rest. In scientific terms, that calm comes from repetition. The aurora pulses at frequencies our eyes cannot always track, but our bodies respond to. Brain and heart rate often slow, slightly under rhythmic visual motion, a biological echo of ancient attentiveness. When the environment quiets, the mind does too. The polar night, with its long pauses between events, teaches the same principle that sleep depends on. When external energy lessens, internal balance returns. The old myths described this transition intuitively. They spoke of the aurora as a messenger between states, between worlds, between waking and dream. Today we know that the lights are plasma guided by magnetism, yet the metaphor remains accurate. Energy crosses a threshold, releases what it holds, and fades into peace. It is a story told not in words but in color, the physics of renewal played out across the sky. As dawn approaches and the arcs dissolve, darkness reclaims the horizon. The silence that follows is complete, not empty but full of rest. Just as the atoms return to their ground state after giving off light, the mind, too, finds its lower energy level. What begins as brightness ends as calm, both in air and thought. When the Enlightenment dawned in Europe, curiosity about the natural world began to replace superstition with measurement. The aurora, once a symbol of divine emotion, became an object of study. Explorers, scholars, and navigators turned their eyes from myth to data, trying to record not just what the lights looked like, but when and where they appeared. The pursuit of understanding became the new form of reverence. In the early 18th century, astronomers across northern Europe began keeping systematic logs of auroral sightings. Olof Hiorter in Sweden and Anders Celsius, whose name later defined the temperature scale, measured fluctuations in magnetic needles whenever the sky glowed. They discovered that auroras were accompanied by measurable disturbances in Earth's magnetic field, a hint that invisible forces linked the ground and the heavens. These findings marked the first true bridge between physics and the spectacle above. At nearly the same time, the English astronomer Edmund Halley speculated that the aurora might arise from magnetic interactions between the Earth and the Sun. Though his details were incomplete, the intuition was correct. A century later, Norwegian physicist Christian Birkeland built on these ideas, conducting experiments that replicated auroral patterns inside a vacuum chamber. By placing a magnetized sphere, his model Earth, within a stream of electrons, he created tiny glowing rings around its poles. The resemblance to real auroras was unmistakable. Birkeland's terrella, or Little Earth, demonstrated that charged particles following magnetic lines could indeed make light. Throughout the 19th century, improvements in optics and chemistry deepened this understanding. Spectroscopy, newly developed, allowed scientists to separate auroral light into its component wavelengths. Each color revealed a specific atomic source, confirming that the green glow came from oxygen and the purple hues from nitrogen. With this knowledge, the aurora was no longer just a phenomenon. It was a laboratory in the sky where atomic physics could be observed on a planetary scale. Even as these breakthroughs unfolded, the human side of observation remained unchanged. Researchers camped through freezing nights, sketching and noting every flicker by hand. Some traveled with expeditions to the far north purely to see the lights in their full intensity. Their diaries describe exhaustion, cold, and awe in equal measure. The measurements were careful, but the language they used remained poetic. Science and wonder did not compete, they intertwined. By the turn of the 20th century, the connection between the aurora and solar activity became undeniable. Telegraph systems, the lifeline of global communication, occasionally failed during bright auroral displays. Engineers found that currents induced by magnetic storms traveled through long wires, overwhelming circuits. Each failure was a clue. The sun, far away and silent, could reach into human technology. The aurora was not a distant curiosity, but part of a living system that included Earth and everything built upon it. Today, scientists regard those early centuries as the foundation of space physics. Each handwritten note, each line drawn under lamplight, contributed to the map we now use to understand the magnetosphere. Yet the spirit behind those first steps was not so different from the myths that came before. Both sought meaning in motion and color. Both began with wonder and ended in pattern. The difference is that science can keep the wonder and measure it too. When we trace the history of discovery, the aurora teaches a quiet lesson. Knowledge is not the opposite of awe, it is its continuation. Each equation is a form of respect, each experiment a way to listen more closely to the universe's calm explanations. What once felt supernatural turns out to be natural in the deepest sense, an expression of the same physics that shapes every star, every atom, and every light in the sky. As the 20th century unfolded, science gained the tools to reach beyond the limits of sight. Balloons, rockets, and satellites would reveal what no telescope could: the true structure of Earth's magnetic environment. The aurora, once only visible from the ground, could now be seen from above. Through these new eyes, the magnetosphere, the invisible shield that directs and shapes the aurora, emerged as a vast and dynamic system. In the early years of the space age, researchers launched small rockets equipped with magnetometers and particle detectors into auroral zones. Each flight lasted only minutes, but the data were revolutionary. They confirmed that electrons streaming down magnetic field lines caused the lights below, and that currents flowed upward as well, completing enormous electrical circuits between the ionosphere and outer space. These discoveries turned the aurora from a spectacle into a living map of energy transfer between sun and planet. Then came satellites. Missions such as Explorer, OGO, and later Dynamics Explorer and Cluster provided continuous coverage of the magnetosphere. Their instruments traced boundaries: the bow shock where the solar wind slows, the magnetopause where pressures balance, and the magnetotail that stretches millions of kilometers into space. Inside these regions, scientists found plasma sheets, particle traps, and layers that breathe with solar activity. When the sun grows restless, these structures shift, storing energy until sudden reconnection events release it toward the poles, lighting the aurora once again. From this growing dataset emerged a picture both intricate and elegant. The magnetosphere is not a fixed shell but a constantly adjusting volume, expanding and contracting like a lung. Its currents follow predictable paths, yet no two moments are identical. Computer models now simulate its behavior using the equations of magnetohydrodynamics, fluid dynamics extended to conductors of electricity. Through these models, scientists can visualize invisible phenomena: lines of force weaving through plasma, waves rippling along boundaries, and energy cascading from solar wind to atmosphere in a controlled, rhythmic flow. Auroras, in this framework, are the visible edges of an enormous electrical system. They are where the current meets resistance and transforms kinetic energy into light. This understanding connects the quiet sky of night to the machinery of stars. What begins with magnetic storms on the Sun ends as delicate motion above Earth's poles. Between those points lies a complete circuit, millions of kilometers long, sustained by the same principles that light every star in the galaxy. Observations from orbit have also revealed symmetry. When auroras brighten in the north, simultaneous emissions appear in the south. These conjugate auroras prove that the magnetosphere's field lines link both hemispheres directly, binding them into one electromagnetic whole. The two ends of the planet respond to the same pulse from the Sun, separated by distance but united in timing. It is a planetary heartbeat, recorded in data yet visible as beauty. As with all science, mapping the magnetosphere has not ended mystery, it has refined it. The more precisely we see, the more intricate the patterns become. Each new satellite reveals layers within layers, waves within waves. The universe, it seems, rewards attention with depth. The closer we look at order, the more we find. And still, beneath all this structure, the sky remains what it has always been, calm to the eye, graceful to the mind. The equations may describe it, but the experience of watching light ripple across a silent horizon belongs to another kind of understanding. Knowledge and wonder meet there, perfectly balanced, like the magnetic lines themselves, curved, continuous, and endlessly returning to their source. When astronauts first looked down from orbit, they saw the aurora from a perspective no one on Earth had known. From space, the lights do not arch overhead. They form rings that encircle both poles, glowing softly against the black curve of Earth. The sight astonished the first crews aboard the International Space Station, who often paused their work to watch green and red ovals drifting beneath them. Cameras captured what eyes could barely hold, rivers of light flowing across continents, faint but constant, the visible trace of an electrical planet. Satellites designed for research turned those moments of wonder into data. Equipped with photometers, particle detectors, and magnetometers, they measured the precise intensity and timing of auroral events. From this information, scientists built a continuous record of how energy from the Sun moves through the magnetosphere and into the upper atmosphere. Each pass of a satellite adds new detail: electron velocities, field strengths, chemical composition of ionized gases. Together they reveal that the aurora is not an isolated event but an ongoing dialogue between star and planet, a flow of energy as steady as ocean tides. Viewed from orbit, the structure of the auroral oval becomes clear. It forms a complete band around each magnetic pole, typically about 3,000 kilometers wide. When solar activity increases, these ovals expand toward lower latitudes. When the Sun quiets, they contract again. The motion is symmetrical, as though the planet inhales and exhales in response to distant flares. Spacecraft instruments record this rhythm in numbers, but the pattern remains unmistakably organic. The advantage of this global view is precision. Ground observers see only a small part of the display, limited by weather and horizon, but satellites watch entire hemispheres at once. Using ultraviolet and X-ray sensors, they can detect auroral activity even in daylight, when it is invisible to human eyes. These observations link the visible lights to invisible phenomena: currents that stretch far into the magnetotail, bursts of plasma that travel along field lines, and waves that carry energy like sound through the charged atmosphere. By combining data from multiple satellites, scientists reconstruct how the aurora evolves in real time. They can follow a solar eruption from the Sun's surface to the instant it touches Earth's magnetic field. This continuous chain of observation forms the basis of space weather forecasting, a field that protects satellites, astronauts, and electrical grids from sudden solar storms. What once seemed a purely visual wonder now serves practical purpose, turning beauty into early warning. Yet, the human response to these orbital images remains emotional. Astronauts often describe a sense of serenity while watching the lights drift below. The planet, they say, looks alive, a breathing organism wrapped in color. In those moments, the distinction between science and feeling disappears. The data streaming through instruments are the same processes that create the view through the window. Measurement and awe are two ways of touching the same truth. From that height, the aurora defines Earth as much as its oceans or clouds do. It shows that our world is not isolated, but part of a vast electromagnetic system connected to the sun. Each flash of light marks an exchange of energy that sustains the balance between radiation and protection, exposure and shelter. To see it from above is to glimpse the planet's pulse, steady and luminous in the dark. When the station passes out of range and night returns, the rings fade to shadow, but the current continues to flow unseen. The Earth remains under observation, not only by instruments, but by its own quiet harmony, the steady conversation between motion and rest that defines all living systems. The northern lights are not confined to Earth. Across the solar system, other planets with magnetic fields host their own versions of the aurora. Each follows the same fundamental laws: charged particles guided by magnetic lines into thin atmospheres, but each world shapes the phenomenon in its own way. Studying these alien auroras reveals both the diversity of planetary environments and the unity of the physical rules that govern them all. Jupiter's auroras are the most powerful known. Its magnetic field is 14 times stronger than Earth's, and its rotation so rapid that magnetic forces sweep through space like invisible blades. The volcanic moon Io adds to this system by releasing plumes of sulfur and oxygen that become ionized and trapped in Jupiter's magnetosphere. When these ions follow field lines into the planet's atmosphere, they produce ultraviolet emissions far brighter than anything seen on Earth. To instruments aboard the Juno spacecraft, the Jovian aurora appears as twin ovals pulsing in time with the planet's rotation, a vast electromagnetic circuit powered by both sunlight and moonlight. Saturn's lights are gentler but equally intricate. Here, the solar wind plays a larger role. The planet's magnetic field aligns closely with its rotation axis, so auroras appear as graceful circles around the poles. Observations from the Cassini spacecraft show that Saturn's auroras glow mainly in ultraviolet, invisible to human eyes but striking to cameras. They brighten when solar storms arrive, fade during quiet periods, and sometimes form spiral patterns that mirror the structure of Saturn's rings. The planet itself acts like a conductor in space, turning solar energy into atmospheric light. Farther out, Uranus and Neptune demonstrate how magnetism can vary. Their fields are tilted dramatically, offset from their centers, and twisted by uneven rotation. As these worlds spin, their magnetic axes sweep through space like wobbling tops, causing auroral regions to wander across the surface. This makes their lights unpredictable, sometimes near the poles, sometimes near the equator. The Voyager missions glimpsed faint hints of these distant displays, confirming that even under weak sunlight, charged particles still find paths to glow. Mars, by contrast, offers an example of absence. Its global magnetic field faded long ago when the planet's core cooled. Only isolated magnetic patches remain in the crust, forming local auroras that appear as scattered spots rather than rings. Observations by the MAVEN mission reveal that these localized emissions still follow the same process, solar wind electrons colliding with the atmosphere. But without a global field to guide them, the lights have no symmetry, no pattern, a reminder that magnetism is not just decoration but defense. Comparing these worlds allows scientists to test how magnetospheres evolve. Strong fields produce stable, ring-shaped auroras. Weak or tilted fields yield shifting, fragmented patterns. By studying their shapes and energies, researchers infer the composition of planetary cores, the strength of internal dynamos, and the interaction between stellar wind and atmosphere. Auroras, in this sense, become diagnostic tools, natural experiments conducted across millions of kilometers. Viewed together, these alien lights trace the same principle that shapes ours. Energy seeks equilibrium, and in doing so, it radiates beauty. From the fierce ultraviolet flares of Jupiter to the fragile red glimmers above Mars, each display is a translation of the same universal dialogue between matter and motion. The aurora is not Earth's alone. It is a cosmic habit, repeated wherever magnetic fields meet wind and air. When astronomers watch these distant ovals brighten and fade, they see reflections of our own sky. Across space, the choreography remains familiar, curtains of light marking the boundary between chaos and order. In that symmetry lies reassurance. The rules that sustain our world are written everywhere, unbroken and calm. No two magnetic fields in the solar system are quite the same. Each planet's field is a fingerprint of its internal motion, how molten metals move within the core, how fast the body spins, and how heat escapes from within. Studying these differences helps scientists understand why some worlds glow with auroras while others remain dark. It also shows that magnetism is not a universal gift, it is a privilege born from planetary vitality. Earth's field, though modest in strength, is remarkably balanced. Its poles are near the axis of rotation, and its dynamo, a fluid flow of molten iron in the outer core, runs smoothly. The result is stability, an organized magnetosphere that channels solar energy into predictable auroral ovals. This alignment may seem ordinary, yet in cosmic terms it is rare. The regularity of our field gives both protection and pattern, the two qualities that make the aurora a gentle companion rather than a violent storm. Jupiter's field is far stronger, but also more chaotic. Driven by a layer of metallic hydrogen under immense pressure, its magnetosphere extends millions of kilometers, enveloping its moons. Here, magnetism dominates gravity. Particles from Io's volcanoes spiral through space, guided more by field lines than by orbits. The auroras that result are immense and constant, their energy measured in terawatts. In contrast, Saturn's near-perfect alignment produces a quieter display, its lights almost circular, modulated more by the sun's wind than by internal turbulence. Uranus and Neptune are the most unpredictable. Their magnetic poles are tilted more than 40 degrees from their rotation axes, and the centers of their fields are offset by thousands of kilometers. As these planets spin, their magnetic geometries twist through space, causing auroras to migrate across the surface in complex loops. On Uranus, the pattern changes daily. On Neptune, it shifts with every rotation. These irregular fields suggest that their dynamos lie in shallow layers of conductive water and ammonia rather than deep metallic cores. The aurora, again, becomes a clue to what lies unseen inside. Venus and Mars, though neighbors to Earth, tell the opposite story. Neither maintains a strong global field. Venus spins too slowly for a vigorous dynamo, and Mars's small size allowed its core to cool long ago. The absence of magnetism exposes their atmospheres directly to the solar wind. Over billions of years, this exposure has stripped much of their air away. What remains are faint traces of localized magnetic zones on Mars and none at all on Venus. Their skies hold no broad auroral curtains, only occasional, scattered glimmers where solar particles strike unprotected air. Comparing these systems, scientists see a continuum of possibility. At one extreme, Jupiter, a magnetic giant whose field dominates the outer solar system. At the other, Mars, a silent world where the wind blows unhindered from the sun. Between them lies Earth, a balance point where magnetism is strong enough to defend life, yet gentle enough to reveal beauty through light. That middle ground, dynamic but stable, may be the key condition for long-term habitability. Magnetic fields do more than create auroras. They preserve atmospheres, deflect cosmic rays, and guide biological navigation. Without them, many of the delicate equilibriums we take for granted would falter. In that sense, to study planetary magnetism is to study survival itself. The aurora is simply the visible side of an invisible shield, proof that the planet still breathes, still moves, still protects. And across the solar system, wherever a world can still move inside, its lights still burn. Magnetism writes its story in color and motion, a spectrum of vitality spanning from deep cores to distant skies. Each planet's glow, however faint or fierce, affirms the same truth, that order arises from movement, and that within motion, peace can still be found. The same forces that paint the sky with color can also disturb the quiet machinery of modern life. When energy from the sun intensifies, it becomes what scientists call space weather, a set of conditions that ripple through Earth's magnetic field, altering currents, signals, and radiation levels. The aurora is the visible trace of this invisible process, a sign that the planet is responding to a surge of energy. Space weather begins with solar activity, flares, coronal mass ejections, and streams of fast-moving plasma from coronal holes. These events hurl charged particles into space at speeds exceeding 1,000,000 kilometers per hour. When this solar wind reaches Earth, the magnetosphere compresses and vibrates like a struck bell. Electric currents flow through the ionosphere, and particles rush toward the poles. Instruments on the ground record these fluctuations as geomagnetic storms, the same events that fill the sky with light. For most people, these interactions pass unnoticed, yet the planet's electrical environment changes measurably. Variations in the magnetic field can induce currents in power lines, disrupt satellite navigation, and distort radio transmissions. Airlines reroute flights during severe storms to avoid excess radiation at high altitudes. Even under calm conditions, engineers monitor solar activity continuously, because a single large flare can send a wave of charged energy capable of disabling technology across half the globe. Scientists track space weather with a global network of satellites positioned between Earth and the Sun. The Solar and Heliospheric Observatory and NASA's DSCOVR satellite measure the density and speed of incoming plasma, providing up to an hour of warning before it reaches Earth. This early notice allows power companies and communication networks to protect sensitive systems. In a sense, the aurora becomes more than spectacle. It is also a natural warning light, a visual index of the sun's temperament. The same rhythm that drives these cosmic fluctuations also finds echoes in human biology. Our bodies, too, follow cycles of energy and calm. When magnetic activity increases, some studies have noted small shifts in sleep patterns or heart rate variability, though the effects are subtle and still debated. What matters more is the metaphor. Just as the magnetosphere balances storms through elasticity, so the mind balances its own surges through rest. In both systems, stability is achieved not by resisting motion, but by absorbing it and returning slowly to equilibrium. If you are listening as night deepens and sleep begins to draw near, you can let this parallel guide you. Think of the magnetosphere surrounding the Earth, flexible, steady, enduring. Imagine your own thoughts as particles moving through that field, gradually slowing, finding their path toward stillness. Like the planet itself, you are shielded by patterns older than memory, held within invisible geometry that knows how to recover. There is no need to force calm. It is already there, waiting behind the noise. From a scientific view, Earth's recovery after each geomagnetic storm is remarkable. Within hours, the field restores its symmetry, and the ionosphere settles back into regular flow. Data return to baseline, satellites resume their quiet orbits, and the aurora fades to a faint glow. The cycle closes, disturbance becomes order, energy becomes light, and light becomes rest. Space weather may never stop, but its pattern is dependable. The sun's activity waxes and wanes, and Earth answers with grace. It is the same with sleep. Energy arrives, builds, releases, and finds stillness again. Both are part of the same rhythm of renewal that defines life under the stars. To understand the aurora fully, scientists must not only observe it but also predict it. Just as meteorologists forecast weather in the lower atmosphere, space physicists forecast the motion of charged particles that shape the upper one. The task is complex. Unlike air, plasma is influenced by magnetic fields, electric currents, and the sun's ever-changing energy. Yet prediction is possible because every disturbance leaves a trace, and those traces follow patterns written in physics. Modern forecasting begins with the sun. Telescopes on Earth and in orbit continuously photograph its surface in multiple wavelengths, recording flares, dark sunspots, and the bright plumes that mark coronal mass ejections. When an eruption occurs, scientists calculate its velocity and direction using stereoscopic images from satellites positioned around the sun. If the ejection is aimed toward Earth, its estimated arrival time can be predicted within a few hours. This gives the first signal that auroras may intensify. The next step happens halfway between the Sun and Earth, where monitoring satellites like DSC-VR and ACE sit at the gravitational balance point known as L1. Here they measure solar wind speed, density, and magnetic orientation. If the wind's magnetic field points southward, opposite to Earth's northward field, the two can reconnect efficiently, transferring energy into the magnetosphere. This alignment is the trigger condition for strong auroras. When instruments detect it, forecasters issue alerts within minutes. Computer models then take over. Using real-time data, they simulate how solar particles will move through the magnetosphere and where the resulting auroral ovals will form. These visualizations, updated every few minutes, are published online for pilots, satellite operators, and the public. Many aurora enthusiasts follow them closely, planning trips to northern latitudes when predictions rise above certain thresholds. In this way, forecasting connects professional research with human experience, turning equations into anticipation. The physics behind these models relies on Maxwell's equations and magnetohydrodynamics, the same laws that describe electric motors and plasma reactors. By solving them numerically, scientists can predict not only the intensity but also the shape of auroral displays. Although uncertainties remain, solar wind turbulence, local atmospheric conditions, the accuracy continues to improve. Today's forecasts can often pinpoint the best viewing hours within a single night. Behind each number lies a network of cooperation. Observatories share data across continents. Amateur sky watchers send photographs that confirm locations. Astronauts report brightness from orbit. The system functions like a living organism, sensing, communicating, adjusting. Each piece of information refines the collective understanding of how the Sun and Earth exchange energy. The goal is not control, but harmony, predicting enough to prepare, while still allowing wonder to surprise. For scientists, this predictive power transforms the aurora into a diagnostic instrument. By comparing forecasted patterns with actual observations, they can test the accuracy of physical models and refine them further. The process is circular. Prediction leads to observation. Observation leads to correction, and correction deepens understanding. In that sense, auroral research mirrors the behavior of the magnetosphere itself, flexible, adaptive, always returning to balance. Forecasting, though rooted in mathematics, carries a quiet emotional resonance. It reminds us that even the most unpredictable beauty follows rules, and that learning those rules does not diminish its grace. When a flare erupts on the sun, It takes roughly 2 days for its energy to reach Earth. During that time, scientists watch, calculate, and wait, knowing that light will soon bloom above the poles. Knowledge and patience merge. Data becomes expectation, and expectation becomes light. Every aurora that sweeps across the sky is fleeting, yet through technology it can now be preserved in extraordinary detail. Cameras, sensors, and telescopes together form an archive of light, a visual record of Earth's magnetic pulse. Each image is more than art. It is data, revealing how energy moves, how the upper atmosphere responds, and how fragile the connection is between space and air. Photographing the aurora is unlike capturing any other natural scene. The lights shift faster than the human eye can adapt, and their brightness changes by the second. Long exposures reveal colors invisible to sight, violets and deep reds that the retina cannot register in low light. Modern digital sensors are sensitive enough to record these wavelengths, transforming what was once a private experience into something that can be studied and shared. When combined into time-lapse sequences, the patterns of movement become clear, showing waves and spirals that reflect the flow of plasma above. Scientists use specialized cameras known as all-sky imagers, equipped with fisheye lenses to capture the entire dome of the heavens. These instruments take continuous photographs throughout the polar night, creating sequences that map the aurora's motion minute by minute. By comparing frames from stations hundreds of kilometers apart, researchers can calculate the altitude and speed of each luminous structure. What seems random becomes measurable, a dance converted into geometry. Spectrographs add another dimension. Instead of pictures, they capture the intensity of light across wavelengths, allowing the identification of atomic species and energy levels. From such spectra, scientists can reconstruct the altitude of emissions and estimate the energy of incoming electrons. When combined with satellite readings, these observations create a complete profile of an auroral event, from solar origin to atmospheric response. Every photon carries a trace of the journey it has taken, and in collecting them, researchers read the story backward. Amateurs contribute as well. With digital cameras and guiding apps, countless observers record auroras from Iceland, Alaska, Finland, and Canada. Their photographs, posted online, often include time and location data that feed into citizen science databases. The global record of auroral images now extends to millions of entries, offering researchers a chronological map of solar cycles and geomagnetic storms across decades. Each photograph, regardless of its artistic intent, becomes a small contribution to understanding how Earth responds to its star. From a visual standpoint, these images reveal details that even standing beneath the sky cannot. Slow exposures show fine threads and arcs within the light, like filaments in a living tissue. In some photographs, you can see the faint red glow high above the green band, or the delicate blue fringe near the horizon. These layers correspond exactly to the altitudes predicted by atmospheric models, confirming that beauty and measurement can coexist perfectly. Recording the aurora has changed the way people experience it. What was once transient can now be replayed, studied, and shared across the world. Yet the essential feeling remains. Even the clearest photograph cannot capture the quiet motion of real light, nor the sensation of cold air and distant stars. The camera measures photons, but the mind remembers calm. When scientists review the data, they often speak of the aurora as if it were alive, breathing, pulsing, reacting. In the language of physics, it is only plasma responding to fields, but in the language of perception, it is movement made gentle. The camera freezes it, but the truth of the aurora lies in change itself, energy transforming, light fading, and order returning. To capture that is not to stop time, but to witness how it flows. The spectacle of the aurora begins not with light, but with chemistry. Each shade that glows above the poles arises from the unique way atoms and molecules in the upper atmosphere store and release energy. Understanding these microscopic exchanges transforms the sky's beauty into a precise sequence of reactions, an illuminated chemistry lesson written across the night. The main players are oxygen and nitrogen. When high-energy electrons from the magnetosphere strike these gases, they transfer part of their kinetic energy to the atom's outer electrons. This pushes the electrons into higher quantum states, temporary configurations of energy. Within a fraction of a second, the excited atoms relax to lower levels, emitting photons at specific wavelengths. The color of each photon reveals exactly how much energy was lost. What we see as green, red, or violet is therefore a direct measure of atomic transition. At altitudes between 90 and 150 kilometers, atomic oxygen dominates. Its most famous emission occurs at 557.7 nanometers, pure green light. Slightly higher, near 200 kilometers, another transition at 630 nanometers produces crimson red. These forbidden lines, as physicists call them, occur only where collisions are rare. Nearer the ground, where air is denser, nitrogen molecules take over. Their complex structure gives rise to blues and purples, produced when electrons excite molecular bands rather than single atoms. Together these emissions form a layered palette, a vertical rainbow sculpted by altitude. Scientists analyze these colors with spectrometers that disperse incoming light into its wavelengths. By comparing intensities, they can estimate both temperature and density of the upper atmosphere. For instance, a stronger red-to-green ratio indicates thinner air and higher altitude. Because these measurements can be made from the ground, auroral spectroscopy provides a non-invasive way to study regions of the atmosphere beyond the reach of balloons or aircraft. Every flash of color becomes a data point in the global study of space weather. The chemistry also explains why auroras vary from night to night. The type of particles arriving from the solar wind, whether electrons or protons, determines which atoms are most excited. Electron precipitation favors green and violet emissions, while proton precipitation often produces diffuse red glows, known as proton auroras. Temperature, atmospheric composition, and solar activity all shift the balance. What the eye perceives as artistic variation is in fact chemical diversity shaped by magnetic dynamics. Laboratory experiments replicate these reactions on a small scale. When scientists pass electrical currents through chambers of rarefied gas, they recreate the auroral spectrum in miniature. Comparing laboratory spectra with those recorded in the sky verifies theoretical models of excitation and de-excitation. The match is exact, the same wavelengths, the same ratios. It is one of the most satisfying correspondences in science, proof that the laws governing a sealed glass tube also govern the heavens. Beyond data, the chemistry of color carries quiet symbolism. Green marks balance, red marks release, violet marks transition. Each is the visual outcome of an atom's effort to regain equilibrium. Energy arrives, is absorbed, and departs again as light. The process repeats endlessly, invisible by day, luminous by night. What begins as motion of charged particles ends as photons moving calmly through the air, reminding us that even in complexity, nature tends toward restoration. When observers watch the sky change from green to red and back again, they are witnessing energy's most graceful transformation. No sound accompanies it, only the soft rhythm of light returning to rest. In that simplicity lies both science and solace, proof that the universe, at every scale, prefers balance to chaos, and reveals that preference in color. Behind every photograph of the aurora stands an array of instruments measuring what no eye can see. The visible glow is only the surface of a much larger system of electric and magnetic activity stretching far above the atmosphere. To understand it, scientists rely on sensors capable of detecting invisible fields, particles, and currents. Each reading adds to a model of how energy from the sun becomes light in our sky. The foundation of these studies is the magnetometer, an instrument that measures the strength and direction of magnetic fields. Networks of ground-based magnetometers are scattered across northern and southern latitudes, recording subtle fluctuations as currents surge through the ionosphere. When a geomagnetic storm begins, their needles move in unison. By comparing data from multiple stations, scientists can map how disturbances travel across the planet. These measurements form the numerical backbone of space weather forecasts. Next come particle detectors, carried by satellites and high-altitude rockets. They count electrons and protons in real time, measuring both energy and velocity. These instruments reveal how quickly the magnetosphere responds to solar changes and how deeply the charged particles penetrate toward Earth. Some detectors use thin foils that scintillate when struck by particles. Others use electric fields to bend their trajectories and measure charge directly. Together they convert invisible radiation into numbers that describe motion, density, and composition. Radars offer another perspective. Systems such as the SuperDARN network transmit radio waves into the ionosphere and record how they scatter. Because charged particles alter the reflection, scientists can infer wind speeds, plasma density, and electric currents across vast areas. The data resemble weather maps, with flowing patterns that shift as magnetic storms build and fade. Through radar, the aurora's unseen dynamics become almost tangible, streams of energy visible as movement on a screen. More advanced observations come from satellites in polar orbits, which fly directly through auroral zones. Their instruments detect both the incoming particles and the electromagnetic waves that guide them. By combining satellite readings with ground observations, researchers reconstruct the entire system in 3 dimensions. It is a bit like listening to an orchestra, not just from the audience, but from within the music. Each instrument, magnetic field, electric current, plasma wave, heard separately yet harmonizing into one structure. Recently, scientists have begun using quantum magnetometers, devices so sensitive they can detect variations smaller than 1/1000th of Earth's field. These instruments exploit quantum effects in atoms of rubidium or cesium, whose energy levels shift slightly when exposed to magnetism. The same principles that define atomic clocks now help trace the planet's electromagnetic heartbeat. With such precision, researchers can study how microcurrents ripple through the ionosphere, producing minor auroras invisible to human sight. What emerges from all these instruments is a sense of scale. A faint flicker above a forest might correspond to electrical currents millions of amperes strong, flowing across thousands of kilometers. The aurora, seen from the ground, feels intimate. Measured from space, it becomes vast and mathematical. Yet both views describe the same phenomenon, energy guided into balance by geometry. Every reading, every data set, feeds into our collective understanding of how the sun and earth remain connected. The aurora is no longer merely an image or an event. It is a set of measurable relationships that reveal the precision of natural law. Numbers replace myth, but not meaning. Even stripped of mystery, the pattern remains beautiful, ordered, rhythmic, and quietly exact. To scientists, the aurora is more than a spectacle. It is a working laboratory that nature runs every night. In its shifting light, they can study processes that shape not only Earth's atmosphere but also the behavior of plasma throughout the universe. Every flicker overhead corresponds to forces that operate in stars, nebulae, and galaxies, condensed here into a scale we can measure directly. The upper atmosphere, where auroras form, is a region of plasma, a state of matter where atoms have been stripped of some electrons and respond collectively to electric and magnetic fields. Because plasma dominates the visible universe, understanding it is essential to almost every branch of astrophysics. yet it is notoriously difficult to reproduce under controlled conditions. The aurora solves that problem. It is plasma on a planetary scale, accessible to instruments but governed by the same physical equations that describe distant cosmic phenomena. In this setting, researchers investigate magnetic reconnection, the process where lines of magnetic force break and rejoin, releasing stored energy. The magnetosphere's tail is an ideal arena for such events. Satellites have observed bursts of acceleration there that match predictions from reconnection theory. These insights extend far beyond Earth. The same mechanism powers solar flares and even shapes the magnetic environments of pulsars. In this way, each auroral storm becomes a small demonstration of cosmic energy transfer. Another focus is particle acceleration. Instruments detect electrons speeding toward Earth at tens of thousands of kilometers per second, guided by Alfvén waves, oscillations of plasma that travel along magnetic lines like ripples on a string. These waves, first proposed in the mid-20th century, explain how the solar wind's energy is translated into visible light. Observing them in real time allows scientists to test mathematical models and refine their understanding of how energy moves through magnetized plasma anywhere in the universe. Ground-based radars complement these observations by tracking how ionospheric currents shift under pressure from the solar wind. The data show that the aurora is not a passive glow but a complex feedback system. Electric fields from space generate motion in the ionosphere, which in turn alters the magnetic field, influencing subsequent flows of energy. The cycle repeats continuously, balancing disturbance with recovery. The planet, in effect, conducts an ongoing experiment in self-regulation. Because these processes mirror those in astrophysical objects, the aurora bridges laboratory physics and cosmic observation. Its scale lies between the two, small enough for direct measurement, large enough to display collective plasma behavior. This middle ground gives it unique educational value. Students of physics can observe, in their own sky, the principles that govern the most energetic systems in existence. A night under the northern lights becomes a field lesson in electromagnetism, radiation, and conservation of energy. In recent years, data from missions such as NASA's magnetospheric multiscale have pushed this research to new precision. Flying in tight formation, multiple satellites cross the same region within seconds, capturing reconnection events at unprecedented resolution. The resulting measurements confirm that energy release occurs in milliseconds and that even the smallest fluctuations in magnetic geometry can trigger vast cascades of motion. These findings help predict not only auroras but also radiation storms that affect spacecraft and astronauts. Standing beneath this silent laboratory, it is easy to forget the scale of what is happening. The patterns above may look calm, but they echo processes powerful enough to light stars. Each beam of color is the visible trace of equations in motion, order drawn out of turbulence. In studying it, humanity learns a little more about how the universe manages its energy, not through chaos, but through precise, repeating balance. Every complex system, whether a planet or a person, must alternate between activity and calm. The Earth's magnetic field, though invisible, follows this rhythm faithfully. After each burst of solar energy, it restores equilibrium with patient precision. The same field that channels charged particles toward the poles also knows how to recover when the pressure fades. The aurora's light, dazzling as it seems, is only one half of this pattern, the moment of release before return. Geomagnetic storms begin abruptly but end slowly. As the solar wind weakens, the magnetosphere expands again, allowing trapped particles to escape into space. Currents in the ionosphere subside, the air's glow dims, and the planet's field resumes its quiet shape. Magnetometers on the ground record the decline as a smooth curve, like a heartbeat returning to its resting rate. The calm that follows is not emptiness, it is restoration, a measurable expression of balance regained. Scientists studying this recovery learn how resilience works on a planetary scale. The magnetosphere does not resist force directly, it absorbs and redistributes it, letting tension flow through flexible boundaries. This capacity for adjustment ensures that the system survives every storm. The lesson extends beyond physics. Stability is not the absence of motion but the mastery of it. A planet maintains peace by allowing energy to pass rather than by holding it still. If you are listening as night deepens, you may feel a similar principle at work. The mind, after a day of solar noise, tasks, thoughts, interruptions, naturally seeks its own magnetic rest. As the aurora fades, imagine the same soft withdrawal of energy within yourself. Each breath mirrors the field's recovery, inhaling with quiet expansion, exhaling with release. You are part of the same pattern, governed by the same physics of renewal. Physiologically, rest functions much like the magnetosphere's recovery phase. During sleep, the brain reduces electrical activity in broad networks, preserving only essential currents for maintenance and repair. Heart rate and temperature fall, chemical gradients shift, and energy redistributes through the body. These cycles echo the same alternation seen in nature: burst and calm, tension and release. Both systems depend on rhythm, not stasis. A storm, whether magnetic or mental, is simply energy in transit. From an observational standpoint, the planet's return to equilibrium is beautiful in its own right. Satellites watch as auroral ovals contract toward the poles, their once bright bands softening into diffuse glows. Instruments detect a decline in particle flux, the numbers steadily dropping until background levels resume. Even the sound of geomagnetic activity, converted into radio waves and played through speakers, fades into a low hum. The system has completed its cycle and is ready for the next dawn. In that global quiet, one can sense how connected everything is. The sun rests after its flare, the earth settles after its response, and life beneath the sky aligns unconsciously with that cosmic tempo. The aurora may seem remote, but its pattern is written everywhere, in oceans, in breath, in the regular pulse that slows when calm arrives. To understand it scientifically is to recognize that rest is not escape from activity, but its natural continuation. As you drift towards sleep, let this thought settle. Every system, from magnetosphere to mind, knows how to return to balance. Energy comes, energy goes, and what remains is stillness, precise and complete. The earth does not struggle to find its calm, it simply allows it. You can do the same. The history of auroral research mirrors the broader journey of science itself, moving from wonder to measurement, from description to explanation. Every discovery about the northern lights has built upon centuries of patient observation, each generation refining the questions of the last. What began as sketches in explorers' journals now unfolds as streams of real-time data from satellites. Yet the spirit behind both remains the same: curiosity about light that behaves like thought. Modern understanding rests on layers of collaboration. Ground-based stations record the visible display, while spacecraft measure the solar wind, magnetic fields, and particle flux beyond the atmosphere. These datasets converge in computer models that reproduce auroras with remarkable accuracy. When simulation and observation agree, researchers know they have captured a piece of the system's logic. Each match between model and sky strengthens confidence in the principles that govern the exchange between sun and earth. This integrated approach has revealed subtleties once invisible. Scientists now track how different regions of the magnetosphere contribute to separate auroral structures: the cusp regions near the poles, the plasma sheet in the magnetotail, the ring current encircling the planet. Each part plays a role in the orchestration of light. The aurora, once seen as a single phenomenon, is now understood as many processes working together in symmetry. Technology continues to sharpen that vision. Data from constellations of small satellites, so-called CubeSats, fill in spatial gaps left by larger missions. Machine learning algorithms sift through terabytes of magnetic readings to find patterns no human could notice unaided. Artificial intelligence classifies auroral types by shape and duration, helping scientists link specific structures to underlying solar conditions. The more we record, the more precisely we can predict, and each prediction tested by nature becomes another confirmation of order in motion. Still, understanding does not end at data. The aurora also serves as an entry point into education and imagination. Students learning physics often encounter it as their first glimpse of plasma behavior. Artists draw inspiration from its flowing lines, musicians from its silent rhythm. Museums display high-speed footage of green veils rippling across Arctic skies, translating equations into sensory experience. The line between knowledge and beauty blurs completely. Both illuminate the same truth from different directions. For planetary scientists, auroral research offers clues to deeper questions. Why some worlds sustain atmospheres while others lose them, why certain dynamos persist and others fail. Understanding Earth's magnetic balance helps in the search for habitable exoplanets. When telescopes detect magnetic signatures on distant worlds, the logic first learned from our own aurora guides interpretation. The lights above the poles thus connect us not only to our planet, but to the physics of countless unseen systems beyond it. In every discipline, from astrophysics to environmental science, the lesson is consistent. Patterns reveal principles. The aurora demonstrates that beauty is not chaos but coherence, that randomness gives way to rhythm when seen at the proper scale. The more precisely we measure, the more clearly we perceive harmony. In that sense, the study of the Northern Lights continues the oldest human endeavor, finding meaning in what moves. And when the data are collected, the instruments silenced, and the night resumes its ordinary darkness, what remains is quiet understanding. The aurora needs no witness to perform. It simply follows the equations that define it. Our comprehension adds context, not purpose. Yet, by learning its patterns, we learn something of our own, the capacity to turn curiosity into clarity and observation into calm. Every aurora begins with a signal from the sun, yet it ends in silence. After the storms subside and the sky clears, only the memory of light remains, a faint echo of the dialogue between two celestial bodies. The sun speaks in charged particles. Earth answers in color. Together they perform a conversation that has continued for billions of years, measured not in words but in rhythm. When solar particles approach, the planet's magnetic field reshapes itself to receive them. Lines of force stretch, reconnect, and guide the energy toward the poles. The process unfolds like breath: inhale, compression, exhale, release. This rhythm is as regular as the sun's rotation and as gentle as the turning of night into day. To scientists, it is a flow of plasma. To the human mind, it feels like calm intention in motion. The repetition of these cycles has consequences that reach beyond the atmosphere. Variations in magnetic activity influence radio communication, satellite drag, and even the migration of animals sensitive to magnetic cues. Birds, sea turtles, and salmon all carry biological compasses tuned to the Earth's field. During geomagnetic storms, their paths may waver slightly, yet when calm returns, orientation restores. In this, nature demonstrates the same resilience seen in the field itself. Temporary disruption followed by steady return. If you listen to this as you prepare for sleep, you are aligning with that universal rhythm. Just as the magnetosphere adjusts to the pressure of solar wind, your body adjusts to the rhythm of day and night. Neurons that tracked sunlight through your eyes now quiet themselves, releasing the hormone melatonin, signaling rest. The chemistry of sleep follows patterns as precise as those governing charged particles. Both depend on balance between excitation and release, activity and stillness. Researchers studying circadian biology describe this shift as a form of synchronization. Cells in the brain's suprachiasmatic nucleus act like small oscillators, keeping time with the rotation of the planet. When darkness falls, electrical activity within these cells slows, lowering body temperature and reducing alertness. It is an internal aurora of sorts, electrical currents fading as the system resets. The connection is not poetic metaphor alone, it is literal. Every rhythm in the body traces back, in some way, to the cycles of sunlight that drive the planet's electromagnetic pulse. As auroral light fades from the sky, instruments continue recording subtle traces of motion, weak currents, gentle oscillations in field strength, the afterglow of energy redistribution. Even in this quiet phase, data reveal complexity. The magnetosphere never sleeps. It rests in movement too small for human senses. The line between stillness and motion blurs, just as the line between waking and sleep does when thought begins to drift. If sleep begins to overtake you now, let it. The same forces that balance the earth will balance you. There is no struggle in gravity, no resistance in magnetism, only attraction seeking equilibrium. Imagine the sky above, dark but alive, with faint electric whispers, and feel your own mind settle into that same field of quiet order. The universe has room for both energy and rest. Its rhythm makes space for both. And when the new day arrives and sunlight returns, the dialogue will resume, charged particles meeting air, energy meeting calm. The cycle continues, as constant as breath and as patient as the sky. For now, the planet rests, and so can you. The aurora we see tonight is only the most recent chapter of a magnetic story that began billions of years ago. Long before humans walked under these skies, the planet already carried a field strong enough to shape the path of solar particles. Evidence of that ancient magnetism remains locked within rocks, a record written not in light but in orientation. Each grain of iron-bearing mineral aligns with the magnetic field of its time, freezing a snapshot of direction as the rock cools. Together, these minerals form Earth's magnetic memory. This field has never been static. Geological records reveal that it has reversed polarity hundreds of times, the north and south magnetic poles trading places in slow, irregular intervals. Each reversal takes thousands of years and leaves a symmetrical pattern in oceanic crust. As molten rock rises at mid-ocean ridges and solidifies, its magnetic orientation flips with each epoch. When mapped, these bands form stripes that mirror across the ridge, proof that the planet's outer core acts like a vast, self-sustaining dynamo powered by motion and heat. Understanding this dynamo explains why the aurora exists at all. The outer core, composed mainly of molten iron and nickel, convects as heat escapes from the inner core. These moving metals generate electric currents, which in turn create the magnetic field. Without that flow, the Earth's protective envelope would collapse, and the solar wind would strip away our atmosphere, as happened on Mars. The soft curtains of auroral light are thus the visible evidence that the planet's heart is still turning. Scientists measure changes in the field through networks of observatories and satellites like SWARM and CHAMP. They map not only its strength but its drift, noting how the magnetic North Pole slowly migrates across the Arctic at nearly 50 kilometers per year. These measurements reveal that the field weakens slightly over centuries before recovering, a natural cycle of adjustment tied to convection patterns deep within the core. Even at its lowest points, it remains strong enough to shield life from most cosmic radiation. The dynamo's power lies in feedback. Moving liquid iron generates magnetic fields, which in turn influence how the metal flows. This interaction creates a stable yet flexible system, order sustained by motion. Mathematically, it is modeled using magnetohydrodynamics, the same equations that describe plasma in stars and the aurora itself. From the fiery core to the cool sky, one language governs all: electricity and motion intertwined. Geophysicists can even trace how magnetic changes correlate with climate and evolution. During reversals, the field's strength drops temporarily, allowing more cosmic rays to reach the upper atmosphere. These rays may influence cloud formation and atmospheric chemistry, subtly affecting weather patterns. The link remains under study, but it suggests that the magnetic field's rhythm touches every layer of the planet, from core to cloud. In human timescales, these shifts feel imperceptible. Compasses still point north, auroras still glow at the poles, and life continues as always. Yet the Earth's deep interior is never still. It turns like a great slow current beneath the continents. Each aurora, then, is not just a response to the sun. It is confirmation that the core below remains alive. Light in the sky begins as movement in darkness, rising through rock, air, and magnetism to become color. To look at the aurora is therefore to witness geological history in motion, ancient heat becoming present light. The sky records what stone remembers, and the two together tell the full story of a planet that endures through change. Though auroras occur high above the weather, their presence connects to the broader climate system in subtle ways. The light itself does not warm or cool the planet, yet the energy exchanges that produce it leave fingerprints in the upper atmosphere, where space and air begin to overlap. Scientists studying these interactions uncover how the magnetosphere and atmosphere share energy, shaping conditions far below the visible glow. During geomagnetic storms, vast amounts of energy pour into the thermosphere, heating it by hundreds of degrees. Because the air is thin, this heat does not translate to surface temperature, but it causes the upper atmosphere to expand. Satellites orbiting in low Earth orbit experience increased drag, slowly losing altitude. Engineers must adjust trajectories to compensate, proving that even invisible winds can affect technology. When the energy subsides, the thermosphere cools again, contracting toward equilibrium. This expansion and contraction forms a quiet breathing pattern that parallels the sun's 11-year cycle of activity. The aurora also influences chemistry. High-energy particles colliding with oxygen and nitrogen break apart molecules and create reactive species such as nitric oxide. These compounds drift downward, interacting with ozone layers that protect life from ultraviolet radiation. During periods of intense solar activity, the amount of nitric oxide reaching the stratosphere increases measurably. Though the effect on global climate is small compared with greenhouse gases, it reveals that solar magnetic coupling touches even the air we breathe. Scientists monitor these changes using satellite spectrometers and limb scanning instruments that detect trace gases by their infrared emissions. Data shows seasonal and solar cycle variations in composition, linking the dance of polar light to the slow chemistry of the atmosphere. Models now incorporate this space weather chemistry, integrating magnetospheric processes into long-term climate simulations. The result is a more complete view of Earth, one where energy from above and below converges to maintain balance. The link between auroras and long-term climate lies not in temperature but in rhythm. Solar activity modulates the inflow of particles, which modulates ionization, which modulates minor gases. These patterns repeat with remarkable consistency. Ice core records capturing nitrate layers correspond to centuries of solar maxima and minima, showing that even before instruments existed, the planet recorded its magnetic weather in chemical form. Each thin band of preserved snow is a historical echo of auroral light that once shimmered over ancient skies. Understanding these couplings matters today, as humanity studies climate from multiple angles. While greenhouse gases dominate near-surface warming, space-atmosphere interactions remind us that Earth's environment is not closed. The sun's variability, subtle but continuous, sets the tempo to which the planet's systems adjust. Recognizing that rhythm helps refine satellite calibration, atmospheric modeling, and even predictions of orbital decay, all practical benefits born from understanding a phenomenon once considered purely decorative. Yet beyond data, this relationship carries quiet symbolism. The aurora's reach, from solar wind to stratospheric chemistry, illustrates how connected every layer of the planet truly is. No process stands alone. Light affects air, air affects climate, and climate sustains life. The entire system works as one unfolding equation, each variable responding to the next. To grasp this interconnectedness is to see the Earth not as a set of compartments, but as a single organism exchanging energy with its star. When the night sky glows again, that light is not separate from the air we breathe or the ground we walk on. It is the visible edge of the same continuum that carries sunlight to forests and tides to shorelines. The aurora may flicker at the planet's ceiling, but its pulse runs through every level below. From the earliest stories to the latest satellites, the aurora has reflected a single trait of humanity: curiosity. Across cultures and centuries, people have looked upward and wondered what the moving lights might mean. The explanations have changed, but the impulse to ask has not. The aurora, in that sense, measures not just magnetic energy but the human need to understand. When the first scientists began documenting the lights, their tools were simple: compasses, ink, and patient eyes. They observed patterns, took notes, and built theories from what they could see. That tradition continues today, though the instruments orbit hundreds of kilometers above the Earth and record billions of data points each day. The purpose remains identical: to reveal how nature organizes itself. The process of investigation, refined but unchanged, links every observer in an unbroken chain stretching from ancient storytellers to modern physicists. The power of the aurora lies partly in its accessibility. Anyone can see it. No telescope or training is required. It turns the vastness of space into something intimate and visible. Standing under an aurora is a reminder that the universe is not distant. It touches the air we breathe. The same forces that guide galaxies flow quietly through the atmosphere above our heads. Each display brings the scale of cosmic physics down to human sense, translating equations into light. That visibility has made the aurora a teacher across disciplines. For artists, it shows color as motion. For engineers, it demonstrates the interaction of energy and structure. For philosophers, it represents order within change. In classrooms, students learn to calculate wavelengths and electron velocities from auroral spectra, bridging abstract theory with natural wonder. The Northern Lights offer a living curriculum where curiosity is both method and reward. In the modern era, exploration of the aurora has expanded into community science. Observers around the world contribute photographs, brightness measurements, and timing reports through online platforms. Their input fills geographical gaps left by satellites and provides valuable cross-checks for professional data. This collaboration between scientists and the public forms a new kind of observatory: global, continuous, and inclusive. The aurora, once confined to remote latitudes, now belongs to everyone connected by light and data. The phenomenon also speaks to human emotion. It evokes calm where there might be fear, and awe where there might be routine. People who witness strong auroras often describe an unexpected stillness, as if sound itself paused to listen. This emotional reaction mirrors the physics behind the event: immense power expressed through grace. The magnetosphere channels chaos into structure, the way curiosity channels uncertainty into learning. In both, motion finds direction. Even as technology advances, mystery endures. There are still unanswered questions: how microscopic plasma waves shape the fine texture of light, why certain colors pulse faster than others, how distant magnetic storms ripple through the ionosphere in patterns we barely perceive. These questions keep researchers awake under polar skies, tuning instruments, refining models, watching for a flicker that confirms a theory. Curiosity, like the aurora itself, never really sleeps. It glows on the horizon of knowledge, inviting pursuit. When we watch the aurora today, we see not only nature's power but our own reflection within it, a species driven to observe, measure, and find meaning. The lights are our reminder that wonder and reason are not opposites. They are partners in the same dance. The sky teaches that every mystery, once illuminated, gives rise to new ones, and that learning is an endless orbit, returning always to the same quiet question: why does it glow? The aurora is a reminder that even silence is full of movement. Long after its last ribbons fade, charged particles still circle invisibly above, magnetic lines continue to flex, and the atmosphere breathes in measured rhythm. The spectacle ends, but the process continues. Proof that calm is not the absence of motion, only its gentlest form. From a scientific view, this calm marks the closing of a complete exchange. Solar energy has traveled 93 million miles, touched a magnetic field, and transformed into color. In that journey, energy has changed states many times: radiation to plasma, plasma to current, current to light. What we call beauty is the visible trace of those conversions, the order that emerges when nature finds balance between force and form. Once the storm ends, instruments record the return to baseline. Magnetic readings flatten, particle counts drop, and the upper atmosphere cools. The thermosphere shrinks to its usual altitude, satellites resume smooth orbits, and electrical systems on the ground stabilize. Every parameter slides back towards symmetry, as if the planet is exhaling after holding its breath. It is a measurable serenity, and it reveals the consistency that underlies all apparent chaos. This pattern of renewal repeats across scales. The Earth restores itself after each disturbance. The Sun follows its cycles. Even atoms that emitted photons in the aurora quickly return to ground states, ready for the next excitation. Stability in nature is rarely rigid. It lives in motion that knows how to rest. The same principle governs the human body. Heartbeats, brain waves, and breaths all rise and fall within their own magnetic rhythms, echoing the pulse of the planet that sustains them. If you are lying in the dark now, listening, the sky above you is quieting too. The magnetic field that shields the Earth is steady, arching gently over continents and seas. The air is calm, the currents are slow, and light from distant stars travels undisturbed through the cold of space. You exist inside this vast equilibrium, part of a system designed for continuity. Let that thought ease the mind the way field lines ease into shape after a storm. Sleep comes most easily when we align with these patterns. There is nothing to force. The body already knows the rhythm. Every slow breath mirrors the planet's balance. Every heartbeat echoes the quiet oscillation of magnetic lines returning to rest. The chemistry of calm is simply the physics of stability written small. Even dreams follow those same oscillations, drifting where energy meets stillness. In the end, the aurora teaches that wonder and peace are not opposites. The same forces that create brilliance in the sky also sustain tranquility on the ground. Understanding that connection changes how we see the world, not as a sequence of separate events, but as one continuous flow of energy seeking harmony. The light that danced above the poles is the same energy that warms oceans, drives winds, and fuels thought. It rises, transforms, and returns, forever moving, forever calm. If sleep begins to reach you now, let the image of those lights stay behind your closed eyes, green curtains fading to red, then dissolving into darkness. Somewhere high above, invisible arcs still shimmer where space meets air. They ask nothing of you but rest, the same way the earth rests when the sun turns its face away. The science of the aurora ends in silence, but its meaning continues in every moment of quiet balance. Energy, once fierce, becomes still. Light, once bright, becomes memory. And within that memory lies the calm of knowing that order always returns. We, from Sleepy Stories, wish you a good night.